Hello there, and welcome to the Sleepy Science Channel. If you enjoy calm, carefully explored science that helps you unwind while gently expanding the edges of what you know, please take a moment to like the video and subscribe to the channel. Your support motivates us to continue creating more meaningful videos. And before settling in, dim the lights, get comfortable, and let your mind wander through the calm universe. The biggest galaxy we have ever discovered is so large that your brain will struggle to truly understand it. This is not an exaggeration. This is not dramatic storytelling. This is the honest truth about a cosmic monster that sits over 1 billion light-years away from us, quietly existing in the darkness of space, holding more stars than you could ever count in 1 million lifetimes. If you're anything like me, you probably felt like you had a sense of how big things can get in space. You've seen images of Jupiter towering over Earth. You've heard that our Sun could fit 1 million Earths inside it. You might have even begun to grasp that the Milky Way stretches about 100,000 light-years from one side to the other. But all of that, every comparison you've ever heard, starts to lose its meaning when you discover what astronomers have found hidden in a distant part of the universe. If you enjoy exploring the strangest and most mind-bending ideas about our cosmos, take a moment to like this video and subscribe to the channel. It helps us create more content like this for you, and it shows that you want to keep exploring the universe together. Now, let's set the scene. Our home, the Milky Way, is what scientists call a barred spiral galaxy. It has graceful, curving arms made of stars, gas, and dust, all rotating around a central bulge where a massive black hole resides. From edge to edge, our galaxy measures about 100,000 light-years across. That means, even if you could travel at the speed of light, the fastest anything can move in the universe, it would still take you 100,000 years to go from one side of the Milky Way to the other. And even that is already incredibly difficult to truly comprehend. 100,000 years is longer than modern humans have existed. It is longer than the time since we first learned to paint on cave walls. Longer than every civilization that has ever risen and fallen on Earth combined. And yet, that is just the width of our own little corner of the cosmos. The Milky Way is home to somewhere between 200 billion and 400 billion stars. Each of those stars might have planets orbiting around them, moons circling those planets, asteroids tumbling through space, and comets streaking through the void. Our Sun is just one of those hundreds of billions of stars sitting about 26,000 light-years from the galactic center in a quiet neighborhood called the Orion Arm. Our Sun and its family of planets orbit the center of the galaxy at a speed of about 500,000 miles per hour. Even at that tremendous velocity, it takes our solar system about 250 million years to complete a single lap around the galactic center. Astronomers sometimes call this period a cosmic year or a galactic year. In the entire time that dinosaurs roamed the Earth, our solar system did not even complete one full orbit. The last time our Sun was in roughly this position in the galaxy. The most complex life on Earth was simple marine organisms. That is how vast even our own galaxy is. The space between stars in the Milky Way is almost unimaginably empty. Our nearest stellar neighbor, a small red dwarf called Proxima Centauri, is about 4¼ light years away. That distance is so great that if you shrunk the Sun down to the size of a grain of sand, Proxima Centauri would be another grain of sand sitting about 4 miles away. The space in between would be essentially void, just the faintest wisps of gas and dust and the occasional particle of cosmic radiation. This emptiness is hard to wrap your mind around. We live on a crowded planet, surrounded by billions of other people, sharing space with countless other living things. We are used to density, to things being close together, to the world being full. But step outside our solar system and emptiness becomes the rule. Stars are separated by such vast gulfs that the chance of any two of them colliding by accident is essentially zero. Galaxies can pass through each other without any stars actually hitting one another. Yet somehow, even in all that emptiness, there is enough stuff out there to make hundreds of billions of stars in our galaxy alone. The gas and dust between stars may be sparse, but spread across thousands of light years. It adds up to enormous amounts of material. New stars are forming right now in giant molecular clouds scattered throughout the Milky Way. Places where gravity has pulled enough gas together for nuclear fusion to ignite. Our galaxy is alive with stellar birth, even as old stars burn out and die. When you look up at the night sky from a dark location, that hazy band of light stretching overhead is actually the combined glow of billions upon billions of distant stars in our own galaxy. Ancient people thought it looked like spilled milk across the heavens, which is where the name Milky Way comes from. For most of human history, we assumed that was everything. We thought our galaxy was the entire universe. Different cultures had different explanations for that band of light. The ancient Greeks told stories of milk spilled from the goddess Hera's breast. The Romans called it the Via Lacta, the Milky Road. In India, it was seen as the past souls take on their journey to the afterlife. Aboriginal Australians saw it as a river in the sky. People throughout history have looked up at that same band of light and wondered what it might be. When the first telescopes were turned toward the Milky Way in the 17th century, observers began to realize that the milky glow resolved into countless individual stars, too faint and too numerous to see with the naked eye, but visible through the magnifying power of glass lenses. This was the first hint that our galaxy was far larger and contained far more stars than anyone had imagined. It was not until the 1920s that an astronomer named Edwin Hubble proved that those fuzzy smudges people had been seeing through telescopes were actually entire galaxies themselves, each one containing billions of their own stars, each one impossibly far away from us. That discovery changed everything we thought we knew about our place in the cosmos. Hubble made this discovery at the Mount Wilson Observatory in California, using what was then the largest telescope in the world, a reflector with a mirror 100 inches across. He was observing a class of stars called Cepheidae variables in what was then called the Andromeda Nebula. These stars pulse in brightness with a regular period, and by measuring their apparent brightness and pulsation rate, Hubble could calculate how far away they were. The result was shocking. The Andromeda Nebula was not a cloud of gas within our own galaxy, as many astronomers had assumed. It was roughly 1 million light-years away, far beyond the edges of the Milky Way. It was an entirely separate galaxy, an island universe of stars in its own right. Our galaxy was not the whole cosmos. It was just one galaxy among many. We now know that Hubble's original distance estimate was off by about a factor of 2. The Andromeda Galaxy is actually about 2 million light-years away, not 1 million, but the basic conclusion was correct. The universe was vastly larger than anyone had imagined, filled with countless galaxies, each containing billions of stars. Today, we estimate that there are around 2 trillion galaxies in the observable universe. 2 trillion. That is, a 2 followed by 12 zeros. Each of those galaxies contains billions or even trillions of stars. The numbers become so large that they stop meaning to our human brains. But here is what makes this story interesting. Not all galaxies are created equal. Some are tiny dwarf galaxies with just a few billion stars. Others are massive spirals like our Milky Way or our nearest large neighbor, the Andromeda Galaxy. And then, sitting at the extreme end of the scale, there are the true monsters of the universe. Galaxies so enormous that they make our Milky Way look like nothing more than a speck of dust floating in an empty warehouse. Galaxies come in many shapes and sizes. The most common type in the nearby universe are spiral galaxies like our own, with their distinctive pinwheel arms and flat rotating disks. These galaxies are typically sites of active star formation, with new stars being born in the gas-rich spiral arms. The beautiful structure we see is maintained by a balance between the rotational motion of the disk and the gravitational pull of all the matter within. Elliptical galaxies are another major type. Unlike spirals, these galaxies have no particular structure. They range from nearly spherical to highly elongated oval shapes, and they are populated mainly by old red stars. Star formation in elliptical galaxies has largely ceased as they have exhausted most of their gas supply. The largest galaxies in the universe are almost all elliptical, formed through the merger of multiple smaller galaxies over billions of years. There are also irregular galaxies, which have no defined shape at all. These are often the result of gravitational interactions with nearby galaxies, which have pulled and distorted their structures. The melanic clouds visible from the southern hemisphere are examples of irregular galaxies that are being affected by the Milky Way's gravity. Galaxies are not scattered randomly through space. They are arranged into larger structures. Galaxy groups contain anywhere from a few to a few dozen galaxies. Our own Milky Way is part of the local group, which includes about 80 known galaxies, including Andromeda and dozens of dwarf galaxies. Galaxy clusters are even larger, containing hundreds to thousands of galaxies held together by gravity. And beyond that are superclusters, the largest known structures, vast collections of galaxy clusters stretching across hundreds of millions of light-years. The galaxy I want to tell you about is one of these giants. It carries the rather unremarkable name IC 1101, taken from its listing in a catalogue of celestial objects created over a century ago. But don't let the simple name mislead you. There is nothing ordinary about this cosmic giant. IC 1101 lies at the center of a galaxy cluster called Abell 2029, located in the direction of the constellation Virgo, as seen from Earth. When astronomers point their telescopes toward this region, they observe a massive gathering of galaxies, all bound together by gravity, moving around a shared center. And at the very center of that cluster, dominating everything around it like a cosmic ruler, sits IC 1101. This galaxy is estimated to span somewhere between 4 and 6 million light-years across. Let that truly settle in. Our Milky Way, which already feels unimaginably large, is only about 100,000 light-years wide. IC 1101 is roughly 40 to 60 times larger than our entire galaxy. If you placed IC 1101 where our Milky Way currently sits, it would not just engulf our galaxy, it would swallow our entire cosmic neighborhood. The Andromeda Galaxy, which is about 2 and 12 million light-years away from us, would find itself inside IC 1101's massive body. The Triangulum Galaxy, another neighbor of ours, would to be consumed as well. All of the dozens of smaller dwarf galaxies that orbit around us, places like the Large Magellanic Cloud and the Small Magellanic Cloud, would simply become tiny components of this giant's vast structure. But size is just the beginning of what makes IC 1101 so incredible. This galaxy is estimated to contain around 100 trillion stars. 100 trillion. Our Milky Way has maybe 400 billion stars at most. That means IC 1101 has roughly 250 times more stars than our home galaxy. If you started counting stars in IC 11, 1 star per second without stopping, it would take you over 3 million years just to count to 100 trillion. And that is assuming you never slept, never ate, never took a break of any kind. The story of how we discovered this cosmic giant begins back in 1790, when a German-born British astronomer named William Herschel was systematically scanning the night sky with his telescope. Herschel was one of the greatest astronomers of his era. He had already discovered the planet Uranus several years earlier, and he spent much of his life cataloging thousands of celestial objects that no one had ever documented before. On June 19th of that year, Herschel pointed his telescope toward a region of sky in the constellation Virgo and noticed a faint, fuzzy blob of light. He carefully recorded its position and moved on to the next object. At the time, Herschel had no way of knowing what he was actually looking at. The technology did not exist to measure how far away this object was. The scientific understanding did not exist to recognize that it was an entire galaxy separate from our own. Herschel simply logged it as another nebula, one of many mysterious cloud-like objects scattered across the heavens. For over a century, that faint smudge of light remained a mystery. It was eventually given the designation IC 1101 when it was included in a catalog called the Index Catalog, which was an expansion of an earlier list of celestial objects. Astronomers studied it when they could, but without the tools to understand its true nature, it remained just another entry in a long list of cosmic curiosities. Everything changed in the 20th century when astronomers developed better telescopes and new techniques for measuring cosmic distances. They discovered that IC 1101 was not a cloud of gas within our own galaxy. It was an entirely separate galaxy, mind-bogglingly far away. The light we see from IC 1101 today left that galaxy over 1 billion years ago. It has been traveling through the void of space for more than 1 billion years just to reach our telescopes. When that light began its journey toward us, life on Earth was still mostly single-celled organisms. Complex animals had not yet evolved. The dinosaurs would not appear for another several 100 million years. Every major event in human history, from the first civilizations to the invention of the telescope itself, happened while that ancient light was still crossing the emptiness between galaxies. As astronomers continued to study IC 1101, they began to understand why it was so incredibly massive. This galaxy did not grow to its enormous size through normal processes alone. It became a giant through an act of cosmic violence that has been happening for billions of years. IC 1101 is what scientists call a cannibal galaxy. It has been eating other galaxies. To understand galactic cannibalism, you need to think about how gravity works on the largest scales. Galaxies do not exist in isolation. They are grouped together in clusters, held together by their mutual gravitational attraction. Within these clusters, galaxies move around each other, sometimes passing close by, sometimes colliding directly. When two galaxies get close to each other, their gravity begins to distort their shapes. Stars get pulled out of their normal orbits. Gas and dust get compressed and stretched. If the galaxies are similar in size, they might merge together over hundreds of millions of years, eventually forming a single, larger galaxy. But if one galaxy is much bigger than the other, something different happens. The larger galaxy simply absorbs the smaller one, stripping away its stars and gas, adding all of that material to its own massive body. This is what has been happening to IC 1101 for billions of years. As the largest and most massive galaxy in its cluster, IC 1101 sits at the gravitational center of everything around it. Smaller galaxies that venture too close get trapped by its enormous gravity. They spiral inward, getting torn apart and consumed over millions of years. Each meal makes IC 1101 a little bit bigger, a little bit more massive, a little bit more dominant. Scientists estimate that IC 1101 has undergone at least 76 major mergers over its long history. 76 times another substantial galaxy fell into this cosmic giant and was absorbed into its body. And those are just the major mergers. Countless smaller, dwarf galaxies have also been consumed. Galaxies so small that they barely registered as a meal for this enormous predator. The evidence for this cannibalistic history is written in IC 1101's very structure. When you look at a galaxy like our Milky Way, you see a beautiful spiral pattern. Those spiral arms are regions where stars are actively forming, where clouds of gas are collapsing under gravity to create new stellar nurseries. Spiral galaxies contain large amounts of gas and dust, the raw ingredients needed for forming new stars, and they have a clear, rotating disk with spiral arms. IC 1101 looks nothing like that. It is what astronomers classify as an elliptical galaxy, meaning it has a smooth, oval-shaped form with no spiral arms at all. Elliptical galaxies are formed when spiral galaxies merge together. The intense gravitational forces during these mergers destroy the fragile spiral structure, mixing the stars into a more random, rounded, or elongated distribution. The fact that IC 1101 is an elliptical galaxy tells us that it has gone through so many mergers that any original spiral form it once had has been completely erased. All of those collisions, all of that gravitational turbulence, have stirred the stars together like ingredients in a cosmic bowl. What remains is this smooth, featureless giant, a record of billions of years of galactic accumulation. But there's something even more striking about IC 1101. Despite containing around 100 trillion stars, it is actually a dying galaxy. The stars within it are almost all old. Most are what astronomers describe as red giants or yellow stars, ancient stellar populations that have already used up most of their fuel. Very few new stars are forming inside IC 1101. And at first, that may seem surprising, given its enormous size and mass. You might expect IC 1101 to be a hotbed of stellar activity, but remember how it grew so large. Every time I consumed another galaxy, it also consumed that galaxy's gas supply. Gas is the fuel for star formation. Without gas, new stars cannot be born. Over billions of years of cannibalism, IC 1101 has used up or expelled most of its available gas. The mergers themselves were often violent enough to heat the gas to extreme temperatures, making it expand and escape the galaxy entirely, or to compress it so quickly that it all formed into stars at once in brief, intense bursts of activity. Either way, the end result is a galaxy that is run out of raw material. What remains is a quiet giant, slowly fading into the cosmic night. The stars that exist now will continue to shine for billions of years to come, but as they eventually burn out and die, there will be no new generations to replace them. IC 1101 is like an ancient kingdom that has conquered all of its neighbors, but has no children to carry on its legacy. It is massive, powerful, and utterly magnificent, but it is also approaching the end of its active life. At the very heart of OC 1101 lies something even more incredible than the galaxy itself. Sitting at the center of this cosmic giant is one of the largest known supermassive black holes in the entire universe. Every large galaxy has a supermassive black hole at its core. Our own Milky Way has one called Sagittarius A star, which contains about 4 million times the mass of our Sun. The black hole at the center of the Andromeda Galaxy is even bigger, containing somewhere around 100 million to 200 million solar masses. But the black hole at the center of ICU 1101 is in a completely different category. Scientists estimate that it contains somewhere between 40 billion and 100 billion times the mass of our Sun. To put that in perspective, this single black hole might have 25,000 times more mass than the black hole at the center of our entire Milky Way Galaxy. Let me help you understand just how massive this is. If you could somehow weigh the Earth, you would find it has a mass of about 6 trillion kilograms. That sounds like a lot until you compare it to the Sun, which is about 330,000 times more massive than Earth. Our Sun is a fairly ordinary star, neither particularly large nor particularly small by stellar standards. Now, multiply the Sun's mass by 50 billion. That is roughly how much mass is packed into the supermassive black hole at IC1's center. All of that mass is compressed into a region of space from which nothing can escape. The gravitational pull at the event horizon, the boundary of the black hole, is so intense that even light itself cannot break free. The size of a black hole's event horizon depends on its mass. For a black hole of 50 billion solar masses, the event horizon would have a radius of roughly 150 billion kilometers. That might sound enormous, and it is, but remember that this is a region containing 50 billion times the mass of the Sun, compressed into what is essentially a point at the center. The event horizon is just the boundary beyond which escape becomes impossible. To put this in perspective, our entire solar system, from the Sun to the orbit of Neptune, is about 9 billion kilometers across. The event horizon of AC1's black hole is roughly 16 times larger than our entire solar system. If you place this black hole where our Sun is, its event horizon would extend well beyond the orbit of Pluto, engulfing everything we consider our cosmic home. What would it be like near this monstrous black hole? The physics of such extreme environments is bizarre and counterintuitive. Time itself would pass differently near the event horizon compared to far away. Someone falling toward the black hole would see the outside universe speed up, while an outside observer would see the falling person slow down and appear to freeze as they approach the horizon. From the outside, they would never seem to actually cross the boundary. Inside the event horizon, all directions lead toward the singularity at the center. Space and time themselves become so warped that the concept of escaping becomes meaningless. The singularity, a point of theoretically infinite density, would tear apart anything that fell in, stretching it into long, thin strands, through a process physicists have nicknamed spaghettification. But here is something remarkable. Despite its enormous size and terrifying properties, the black hole at IC 1101 center is currently relatively quiet. It is not actively devouring huge amounts of matter. There is no brilliant accretion disk swirling around it, no powerful jet shooting into space at nearly the speed of light. The black hole is there, waiting, but it has already consumed most of the material that was easily within reach. This quietness is actually related to the same phenomenon that has stopped IC 1101 from forming new stars. Most of the gas in the galaxy has already been used up, and without gas falling toward the center, the black hole has little to eat. Occasionally, a star wanders too close and gets torn apart, providing a brief meal. But these events are rare. The black hole, like the galaxy that hosts it, is a giant in repose, powerful, but dormant. There are still traces of the black hole's past activity. Astronomers have detected a radio source at IC 11101 center, catalogued as PKS 508+059. This radio emission comes from relativistic jets, streams of particles accelerated to nearly the speed of light and ejected from the vicinity of the black hole. These jets are powered by the black hole's rotation and magnetic fields, and they can carve out enormous cavities in the surrounding gas. Images from X-ray telescopes show these cavities clearly. They are bubbles of very hot, very thin gas, blown outward by the energy released near the black hole. Some of these bubbles are millions of light-years across, testimony to periods in the past when the black hole was much more active than it is today. The energy required to inflate these bubbles is staggering, equivalent to the total energy output of billions of stars over millions of years. This kind of interaction between supermassive black holes and their host galaxies is one of the most active areas of research in modern astrophysics. Scientists now think that supermassive black holes play a key role in controlling how galaxies grow and evolve. When gas flows toward the center of a galaxy, the black hole can release enough energy to heat that gas and push it outward, preventing it from forming new stars. This creates a kind of regulating effect, a cosmic thermostat, that helps determine the final size and structure of galaxies. In the case of IC 1101, this feedback is likely part of the reason for its current condition. The black hole has contributed to shutting down star formation by heating the gas and stopping it from cooling and collapsing. The massive galaxy and its enormous black hole have reached a kind of balance, each shaping the other over billions of years of shared evolution. Black holes grow by consuming matter that falls into them. When galaxies merge, the supermassive black holes at their centers eventually move toward one another and merge as well. Over the long history of IC 1101's galactic mergers, its central black hole has been fed again and again. Every galaxy it absorbed added to the mass of this growing giant. Each merger brought in more material to fuel the black hole's relentless appetite. And the process by which two supermassive black holes come together is both complex and violent. When two galaxies collide, their central black holes do not immediately find each other. They are separated by vast distances and surrounded by billions of stars. But as the merger progresses, gravitational friction with the surrounding stars causes the black holes to spiral toward the center of the combined galaxy. Eventually, the two black holes get close enough to form a binary system, orbiting around each other. As they orbit, they lose energy through gravitational waves, ripples in the fabric of space-time itself. These gravitational waves carry energy away from the binary, causing the orbit to shrink. The black holes spiral closer and closer, orbiting faster and faster, until finally they merge in a catastrophic event that releases enormous amounts of energy. When two supermassive black holes merge, the gravitational waves they produce are among the most powerful events in the universe. The final merger releases more energy than all the stars in a typical galaxy combined. Though most of this energy is in the form of gravitational waves rather than light. These waves ripple outward at the speed of light, stretching and squeezing space itself as they pass. We have only recently developed the technology to detect gravitational waves. The first direct detection came in 2015, when the LIGO observatories measured waves from two stellar mass black holes merging about 1 billion light-years away. Since then, dozens of gravitational wave events have been observed, opening up an entirely new way of studying the universe. Future gravitational wave detectors, like the planned LISA mission that will fly in space, will be able to detect mergers of supermassive black holes. When LISA launches, perhaps in the 2030s, it might actually detect events similar to the mergers that built up IC1's central black hole. We will be able to listen to the universe as giant black holes collide and merge, adding another sense to our astronomical toolkit. IC Alert 1's black hole has experienced dozens of such mergers over its long history. Each merger added mass and altered the black hole's spin. The process of multiple mergers also affected the surrounding galaxy, as the merging black holes flung stars outward through gravitational interactions. This is probably why IC 1101's core is so large, yet relatively faint. Repeated black hole mergers have scattered stars away from the very center, creating a chord profile that is unusual for galaxies of this size. The event horizon of a black hole, which is the boundary beyond which nothing can escape, gets larger as the black hole gains mass. For a black hole containing 50 billion solar masses, the event horizon would extend outward for about 150 billion kilometers. That is roughly the distance from our Sun to the outer reaches of our solar system, all contained within a region of space where not even light can escape. Around this supermassive black hole, there is a bright radio source that astronomers have catalogued as PKS 158+059. This radio emission comes from jets of material being blasted outward from the vicinity of the black hole at nearly the speed of light. Even though the black hole is not as active as it once was, it still occasionally flares to life, releasing enormous amounts of energy into the surrounding space. The presence of such an enormous black hole raises fascinating questions about the connection between galaxies and the monsters at their hearts. Scientists have discovered that there is a relationship between the mass of a galaxy's central black hole and the properties of the galaxy itself. Bigger galaxies tend to have bigger black holes. But which came first? Did the black holes form first and then grow their galaxies around them? Or did the galaxies form first and then build up their black holes over time? The answer seems to be that they grew together, each one influencing the development of the other. As IC 1101 consumed more and more galaxies, its central black hole also consumed the black holes from those galaxies. The two processes fed into each other, creating a feedback loop that produced both the largest known elliptical galaxy and one of the largest known black holes in existence. The core of IC 11101 is also remarkable for its sheer size. A study conducted in 2017 using images from the Hubble Space Telescope measured the galactic core and found that it stretches across nearly 14,000 light-years. That means just the central core of IC 1101, not the whole galaxy, but just the innermost region, is bigger than most entire dwarf galaxies. This core alone contains more stars than most galaxies in the universe. Now, I want to take you on a journey to help you truly appreciate the scale of what we are talking about. Imagine you could somehow travel from one end of IC 1101 to the other. You would need to cross somewhere between 4 and 6 million light-years. Remember, light travels at about 6 trillion miles per year. Even at that incomprehensible speed, crossing IC 1101 would take millions of years. But let us try another comparison. The Voyager 1 spacecraft, launched by NASA in 1977, is the fastest human-made object ever to leave our solar system. It is traveling at about 38,000 miles per hour relative to the Sun. At that speed, Voyager 1 would take about 80,000 years just to reach the nearest star to our Sun, Proxima Centauri, which is only about 4 light-years away. To cross the entire Milky Way at Voyager 1 speed would take about 2 billion years. And to cross IC 1101, you would need somewhere between 80 billion and 120 billion years. That is more time than the universe has even existed. Even with our fastest spacecraft, crossing this single galaxy would be completely impossible. Here is another way to think about it. If you could shrink the Milky Way down to the size of a dinner plate, about 10 inches across, then IC 1101 would be the size of a large swimming pool. Our entire galaxy, with all of its hundreds of billions of stars, with the spiral arms where we make our home, would be just a tiny dish floating in a vast sea. Or consider this. Light from IC 11 has traveled for over 1 billion years to reach us. In all that time, light has been continuously streaming away from this galaxy in every direction. Every second, IC 1101 radiates enough light to travel about 186,000 meters. Over 1 billion years, that light has traveled 1 billion light-years, which is about 6 billion trillion miles. And it is only now just arriving at our telescopes. Ancient photons that left their home galaxy when Earth was still in its earlier stages of complex life. The discovery and study of IC 1101 would not have been possible without tremendous advances in telescope technology. In the early days of astronomy, telescopes were limited by the size of their lenses and mirrors. Larger telescopes could gather more light and see fainter objects. But there were practical limits to how big you could make a telescope on the ground. The atmosphere also posed a problem. Earth's atmosphere is constantly moving and shimmering, which is why stars appear to twinkle. This twinkling blurs the images that ground-based telescopes can capture, limiting how clearly they can see distant objects. For most of the 20th century, astronomers could see that IC 1101 existed and was very large, but they could not study its detailed structure. Everything changed with the launch of the Hubble Space Telescope in 1990. Floating above the atmosphere, Hubble could capture images with incredible clarity. Over the decades since its launch, Hubble has observed IC 1101 multiple times, revealing details about its core, its surrounding halo of stars, and its relationship to the other galaxies in its cluster. More recently, astronomers have used a variety of other telescopes to study IC 11101 at different wavelengths of light. Radio telescopes have detected the emission from its central black hole. X-ray telescopes have observed the hot gas that fills the cluster around it. Infrared telescopes have peered through the dust to study the stellar populations within the galaxy. Each new observation adds to our understanding of this cosmic giant, but there is still much we do not know. The exact number of stars in IC 1101 is still uncertain because counting stars in such a distant galaxy is incredibly difficult. The precise size of the galaxy depends on how you define where it ends. Since galaxies do not have sharp boundaries but gradually fade into the darkness of intergalactic space, the mass of the central black hole is known only approximately, because measuring black hole masses at such distances involves many assumptions. What we do know is that IC 1101 represents something close to an upper limit for how large galaxies can get. There may be slightly larger galaxies out there waiting to be discovered. In fact, in 2022, astronomers announced the discovery of a galaxy called Eleonos, which has radio lobes extending across an astonishing 16 million light-years. But Eleonos is a special case. Its enormous size comes from giant jets of material shooting out from its central black hole, not from stars. Today, the supplement and normal galactic material. When it comes to the actual body of a galaxy, the collection of stars and gas and dark matter that make up its substance, IC 1101 remains one of the largest ever found. It sits at the extreme end of the galactic size distribution, a true monster among giants. The story of IC 1101 also reveals something profound about the nature of the universe and the passage of cosmic time. Galaxies don't form all at once. They grow over billions of years through a process of accumulation and merger. Small galaxies form first, from collapsing clouds of primordial gas. Those smaller galaxies then come together to form larger ones. Larger galaxies continue merging to create even bigger systems. And the process goes on, with the largest galaxies growing by consuming their smaller neighbors. This is known as hierarchical structure formation, and it is one of the key principles of modern cosmology. The universe builds from the bottom up, starting small and becoming large through countless mergers over time. IC 1101 is simply one of the most extreme examples of this process that we've discovered so far. It has had billions of years, along with a prime position at the center of a rich galaxy cluster, to grow to its enormous size. But this growth cannot continue forever. IC 1101 has already absorbed most of the galaxies that were close enough to be captured. Those that remain are either too distant or moving too quickly to be drawn in. The surrounding cluster is slowly spreading apart due to the expansion of the universe, carrying potential future mergers farther beyond IC 1101's gravitational reach. At the same time, the broader universe is evolving in ways that will eventually affect every galaxy, including this immense one. Space itself is expanding, and not just expanding, but accelerating in its expansion. This acceleration is driven by something scientists call dark energy, a mysterious force that makes up about 68% of the total energy in the universe, but whose nature we do not understand at all. Let me explain dark energy a bit more, because it is one of the most fascinating and puzzling discoveries in all of science. For most of the 20th century, astronomers assumed that the expansion of the universe was slowing down. This made intuitive sense. Everything in the universe is pulling on everything else through gravity. You would expect all that gravitational attraction to act like a brake, gradually slowing the expansion that began with the Big Bang. In 1998, two independent teams of astronomers made a shocking discovery. They were measuring the expansion rate of the universe by observing distant supernovas, using them as standard candles to calculate cosmic distances. What they found was completely unexpected. The universe was not slowing down. It was speeding up. Distant galaxies were moving away from us faster than closer ones, and the rate of expansion was accelerating over time. This discovery was so unexpected that the astronomers initially thought they had made an error. But as more data came in from more supernovas and from other observations, the result held up. Something was pushing the universe apart, counteracting gravity and causing space itself to expand at an ever-increasing rate. Scientists named this mysterious force dark energy. Though the name tells us very little about what it actually is, we know that dark energy makes up about 68% of all the energy in the universe. We know that it acts as a kind of anti-gravity, pushing space apart rather than pulling it together. We know that its effects become more important over time as the universe expands and ordinary matter becomes more spread out. But we do not know what dark energy is made of, where it comes from, or why it has the strength that it does. It might be a property of empty space itself, something called the cosmological constant that Albert Einstein once proposed and then called his biggest blunder. It might be a new kind of energy field that pervades the universe. It might even be a sign that our understanding of gravity is incomplete and needs to be revised. What we do know is that dark energy is reshaping the future of the cosmos. As space expands faster and faster, distant objects recede from us at ever-increasing speeds. There is a limit to how fast light can travel, but there is no limit to how far space itself can expand. Eventually, objects will be carried away from us by the expansion of space faster than their light can travel toward us. When that happens, they will vanish behind a cosmic horizon, forever beyond our reach. For IC 1101, this means that his days of growth through galactic cannibalism are numbered. Eventually, there will simply be no more galaxies left for it to consume. It will become isolated, a lonely giant floating in an ever-emptying universe, watching as one by one the other galaxies fade from view. Actually, let me paint a more detailed picture of what this future looks like. Remember that IC 1101 sits in the Apple 2029 galaxy cluster, surrounded by hundreds of other galaxies. These galaxies are bound together by gravity, orbiting around their common center of mass. For now, gravity is strong enough to hold the cluster together against the expansion of space. But in about 100 billion years, the expansion will have accelerated to the point where galaxies outside the local supercluster will start to disappear over the cosmic horizon. From IC 1101's perspective, the sky will start to empty. One by one, distant galaxy clusters will fade from view, their light no longer able to reach across the expanding void. The observable universe, which currently contains about 2 trillion galaxies, will shrink and shrink. Within the Able 2029 cluster, things will be different for a while longer. The galaxies there are close enough and bound tightly enough that they will stay together even as the larger universe empties out. Over the next several billion years, these galaxies will continue to interact, merge, and evolve. IC 1101 might still consume a few more victims, growing slightly larger even as the rest of the universe slips away. But eventually, even the galaxies within the cluster will merge together. The same processes that built IC 1101 will continue drawing the remaining galaxies toward the center, where they will be absorbed into an even larger combined structure. In the very long run, perhaps in several 100 billion years, all the galaxies in the AEL 2029 cluster might merge into a single enormous galaxy, even larger than IC 1101 is today. By that time, however, the universe beyond the cluster will be essentially empty. No light from distant objects will be reaching the cluster anymore. The night sky, if any observers still existed, would show only the stars of the local merge galaxy against a backdrop of absolute blackness. The rest of the cosmos would have slipped beyond the horizon, unreachable and unknowable. This is the isolation that awaits IC 1101 and every other structure in the universe. Cut off from everything else by the relentless expansion of space, each island of matter will be alone with itself as the eons roll by. But even this is not the final fate of IC 1101. What happens to a galaxy in a universe that is slowly winding down toward heat death? The answer is as magnificent as it is melancholy. Over the next 100 trillion years, the stars in IC 1101 will slowly burn out. The massive blue stars went long ago, exploding as supernovas or collapsing into black holes. The middle-sized stars, like our Sun, will puff up into red giants, shed their outer layers as beautiful nebulas, and then fade away as white dwarfs. Even the smallest, longest-lived stars, the red dwarfs that burn their fuel so slowly they can shine for trillions of years, will eventually exhaust their hydrogen and go dark. Let me walk through this stellar death in more detail, because the timescales involved are truly mind-boggling. The most massive stars in IC 1101, the blue giants and supergiants, live fast and die young. They burn through their fuel in just a few million years before exploding as supernovas. Any blue giants that IC 1N1 once possessed burned out billions of years ago. The galaxy today is dominated by older, smaller, longer-lived stars. The stars most similar to our Sun have lifetimes of about 10 billion years. Our Sun is roughly halfway through its life, with about 5 billion years left before it swells into a red giant and eventually becomes a white dwarf. In IC 1101, many Sun-like stars have already completed this process, leaving behind white dwarf remnants. Others are still shining, but over the next several billion years, they too will burn out. But the most numerous stars in any galaxy are red dwarfs, tiny stars with a fraction of the Sun's mass. Red dwarfs burn their fuel so slowly that they can shine for trillions of years. A red dwarf born at the same time as our Sun will still be shining long after the Sun has become a cold, white dwarf. In IC 1101, with its 100 trillion stars, there are untold numbers of red dwarfs. These tiny, dim stars will be the last to go out. For trillions of years after the larger stars have died, the red dwarfs will continue to burn, providing the only light in an otherwise darkening galaxy. But even red dwarfs have limits. The smallest red dwarfs, with perhaps 8% of the Sun's mass, can burn for up to 10 trillion years. That is about 700 times the current age of the universe. But eventually, even they will exhaust their hydrogen fuel and fade into darkness. Scientists estimate that star formation in the universe will effectively cease in about 100 trillion years. By that time, the gas and dust needed to make new stars will have been used up or dispersed too thinly to collapse. No new stars will be born to replace the ones that have died. The era of starlight will be over. One by one, the 100 trillion stars of IC 1101 will wink out. The galaxy will grow dimmer and dimmer, over timescales that make the current age of the universe seem like the blink of an eye. Where once there was a blaze of stellar light, there will eventually be nothing but the cold, dark remnants of dead stars, white dwarfs, neutron stars, and black holes drifting through an ever-expanding void. The universe at this stage will be a dark place, but not an empty one. All those stellar remnants, all those white dwarfs and neutron stars and black holes will still exist. They will orbit through the merged remnant of what was once I-1 and its cluster companions. The galaxy will be a ghost of its former self, populated by the corpses of stars rather than by living, burning suns. But even this is not the end. Over even longer timescales, measured in years with so many zeros that writing them out would fill pages, even these stellar corpses will decay. White dwarfs will slowly cool until they become black dwarfs, objects that no longer emit any light at all. This cooling process takes an almost inconceivable amount of time. A white dwarf cools to near absolute zero only after about 10 to the 15th power years, or about 1,000,000 billion years. That is roughly 100,000 times longer than the current age of the universe. Neutron stars might decay as their fundamental particles gradually break down. We are not entirely sure about this because it depends on whether protons, the building blocks of atomic nuclei, are truly stable, or whether they eventually decay. Some theories of particle physics predict that protons should decay with a half-life of around 10 to the 34th power years or longer. If this is true, then over unfathomably long time spans, even the matter that makes up neutron stars and white dwarfs and planets and everything else will gradually dissolve into radiation. And the black holes, including that enormous monster at the center of IC 1101, will slowly evaporate through a process called Hawking radiation. Stephen Hawking discovered that black holes are not truly black. They slowly leak particles and radiation over immense time spans, gradually shrinking as they do so. This happens because of quantum mechanical effects near the event horizon. In the strange world of quantum physics, particle pairs are constantly popping into existence and then annihilating each other. Near the event horizon of a black hole, one particle from such a pair can fall inward while the other escapes into space. Over time, this process draws energy away from the black hole, causing it to slowly shrink. The rate of Hawking radiation is extremely slow for large black holes. A black hole with the mass of our Sun would take around 10 to the 67th power years to fully evaporate. That's a 1 followed by 67 zeros. But the supermassive black hole at the center of IC 1101 is billions of times more massive than the Sun, and the time required for it to evaporate is correspondingly longer. A black hole with a mass of about 50 billion suns could take something on the order of 10 to the 100th power years, or even more, to disappear. That's a Google years, a 1 followed by 100 zeros. Writing out that number in full would require more paper than exists on Earth. It is a timescale so vast that everything we've discussed so far, from the Big Bang to the death of the last stars, barely registers in comparison. But even that span is not infinite. Eventually, trillions upon trillions upon trillions of years into the future, even the supermassive black hole at the center of IC 1101 will radiate away its final energy and vanish in a last burst of Hawking radiation. And when that happens, nothing of IC 1101 will remain. No stars, no black holes, no remnants of any kind. Just the particles and radiation that once made up a galaxy spreading out through an ever-expanding, ever-cooling, ever-darkening universe. The largest galaxy we have ever found will have followed the same ultimate path as every other structure in the cosmos, dissolving into the endless night. This vision of the future might seem bleak, but I find something strangely beautiful about it. IC 1101 exists right now, in this brief moment of cosmic history when stars still shine and galaxies still glow. It has existed for billions of years and will continue to exist for billions more in the grand sweep of cosmic time. The era of stars and galaxies is just a passing phase, a brief flowering of complexity between the chaos of the early universe and the cold emptiness of the far future. We are lucky enough to exist during this flowering. We are lucky enough to have evolved intelligence, built telescopes, and pointed them at the sky. We are lucky enough to have discovered IC 1101 and to understand, at least in part, what it is and how it came to be. In all the vast history of the universe, stretching from the Big Bang to the final heat death, this moment, right now, is special. It is the moment when the universe has developed the ability to look at itself and wonder. And what we see when we look at First Child 1101 is the grandest scale on which the universe has assembled matter into organized structures. We see billions of years of cosmic history written in stars. We see the results of countless galactic mergers, countless collisions, countless acts of gravitational violence that have somehow produced something magnificent. We see a monster, yes, but also a monument. A monument to the forces that shape our universe and to the processes that have been building complexity ever since the first atoms formed. Let me bring us back closer to home for a moment. Our own Milky Way is not immune to the forces that shaped First Child 1101. We too are participating in the cosmic dance of galactic interaction and merger. Right now, as you read these words, our galaxy is in the process of consuming several smaller galaxies. The Canis Major dwarf galaxy is being ripped apart and absorbed into the Milky Way. The Sagittarius dwarf galaxy is being stretched and distorted by our gravitational pull. Streams of stars from past victims can be traced across our sky, ghostly reminders of galaxies that once existed as separate entities. And in the future, an even more dramatic event awaits. The Andromeda Galaxy, our nearest large neighbor, is heading toward us. Scientists have long believed that in about 4 to 5 billion years, the Milky Way and Andromeda would collide and eventually merge into a single larger galaxy, often nicknamed Milka. Recent research has introduced some uncertainty into this prediction. New studies using data from the Gaia spacecraft and Hubble Space Telescope suggest that the collision might not be as certain as we once thought. When scientists account for the gravitational influence of other nearby galaxies, like the large Magellanic Cloud and the Triangulum Galaxy, the probability of a collision drops significantly. Some simulations now suggest only about a 50% chance of a merger happening within the next 10 billion years. But whether it happens in 4 billion years or 10 billion years or not at all, the process itself illustrates the same forces that created IC 1101. Galaxies interact, merge, and consume each other. It is the way of the universe. Even our own quiet corner of the cosmos participates in this cosmic competition. If the merger does happen, the results would be spectacular, at least on cosmic timescales. The collision itself would not be violent in the way you might imagine. Stars are so far apart that the chances of any two stars actually hitting each other are essentially zero. But the gravitational effects would be dramatic. The spiral structures of both galaxies would be destroyed. Gas clouds would be compressed, triggering enormous bursts of star formation. The two supermassive black holes at the centers of each galaxy would eventually find each other and merge, releasing gravitational waves that would ripple across the universe. Over billions of years, the chaos would settle down. What was once the Milky Way and what was once Andromeda would blend together into a single large elliptical galaxy, much like 1C or 111, but much smaller. Future astronomers, if any exist, might look back at old records and marvel that their smooth, featureless home galaxy was once two beautiful spirals dancing through the void. By that time, of course, Earth will be long gone. Our Sun is expected to expand into a red giant in about 5 billion years, swelling to a size that would engulf our planet. Whether humanity survives until then, whether we spread to other star systems, whether intelligence of any kind persists in the universe, these are questions we cannot answer. But the story of IC 1101 reminds us that the universe operates on timescales that dwarf individual lives, individual civilizations, even individual planets. I want to return now to the question of what IC LM01 tells us about our place in the universe. When you look up at the night sky, you might feel small. You might feel insignificant in the face of such vastness. But I think the existence of IC 1101 actually tells us something hopeful about our situation. First, consider that we can know about IC 1101 at all. A galaxy more than 1 billion light-years away containing 100 trillion stars, and we have figured out how big it is, how it formed, what lies at its center. That is remarkable. Human beings living on a small, rocky planet orbiting an ordinary star in an unremarkable part of an average spiral galaxy have somehow developed the ability to understand objects so far away that their light left before complex life existed on Earth. This ability to understand is not nothing. In a universe of mindless matter and energy, of particles bouncing around according to physical laws, somehow, here on Earth, consciousness has emerged. Minds that can wonder, question, investigate, and learn. Whatever else we are the part of the universe that has woken up and started asking questions about itself. Second, consider that IC 1101, for all its enormity, is made of the same stuff we are. The stars in IC 1101 are fusion reactors, just like our Sun. They burn hydrogen into helium and heavier elements, just like stars do everywhere. The atoms in those distant stars are the same kinds of atoms that make up our bodies: carbon, oxygen, nitrogen, iron. All of them were forged in the hearts of stars somewhere in the universe. Just as the atoms in our bodies were forged in stars that exploded before our Sun was born, there is a continuity here, a connection between us and everything else in the cosmos. We are not separate from the universe. We are part of it. The same processes that built IC 1101 built us. The same atoms that shine in distant galaxies shine in our eyes. We are not observers of the universe from outside. We are the universe observing itself from within. Third, consider what it means that galaxies like IC 1101 can exist at all. The universe did not have to be this way. If the fundamental constants of physics were slightly different, if gravity were a little stronger or the nuclear forces a little weaker, stars and galaxies might never have formed. The universe might have collapsed back on itself moments after the Big Bang, or expanded so fast that matter never clumped together. Instead, we live in a universe where physical laws allow for the formation of stars, planets, galaxies, life, and mind. IC 1101 is a testament to what is possible in such a universe. It is proof that matter and energy, following simple physical rules, over billions of years, can organize itself into structures of staggering complexity and beauty. If the universe can produce IC 1101, what else might it be capable of? What other wonders exist out there that we have not yet discovered? This brings me to the final point I want to make about IC 1101 and about our quest to understand the universe. Every discovery we make, every galaxy we study, every black hole we observe, expands our sense of what is possible. A few centuries ago, people thought Earth was the center of everything. Then we learned that we orbit the Sun. Then we learned that the Sun is one star among hundreds of billions in our galaxy. Then we learned that our galaxy is one of trillions. Each step has made us smaller in some sense, but it has also made the universe grander, more interesting, more worthy of all. IC 1101 is another step in that journey. It shows us that the universe can build things far larger than we ever imagined. It challenges us to keep asking questions, to keep looking further, to keep pushing the boundaries of what we know. And it reminds us that for all our insignificance on cosmic scales, we are the ones doing the asking, doing the looking, doing the pushing. In the face of IC 1101's enormity, we can feel small, or we can feel wonder. I choose wonder. As we wrap up this exploration of the biggest galaxy ever discovered, I want to leave you with one final image. Imagine yourself floating in space, somewhere near the edge of IC 1101. Around you, in every direction, stars stretch out toward infinity. Not hundreds, not thousands, not millions, but trillions of stars. Each one is a sun. Each one might have planets. Each one has been shining for billions of years. You cannot see the center of the galaxy from here. It is too far away, hidden behind countless curtains of stars. You cannot see the edge either. The galaxy fades gradually into the darkness of intergalactic space, with no clear boundary. You are lost in a sea of light, adrift in a structure so vast that crossing it would take millions of times longer than human civilization has existed. And yet, from a small, rocky planet more than 1 billion light-years away, beings who live for less than a cosmic instant have figured out that this place exists. They have measured its size, counted its stars, found the black hole at its heart. They have traced its history back billions of years and projected its future trillions of years hence. They have placed it in the context of an entire universe and marveled at its grandeur. That is perhaps the most amazing thing of all. Not that IC 1101 exists, but that we know it does. But before we end, I want to dive even deeper into some of the most fascinating aspects of what we have discussed. Because understanding IC 1101 is not just about memorizing numbers and facts. It is about understanding the fundamental processes that have shaped everything in our universe, including us. Let us talk more about what happens inside a galactic merger. When I say that IC 1101 has consumed dozens of other galaxies, it might sound like a simple process, like one object swallowing another. But the reality is far more complex and far more beautiful than any simple description can capture. When two galaxies begin to interact, the first thing that happens is a gravitational dance. Even when the galaxies are millions of light-years apart, they can feel each other's gravity. This gravity begins to distort their shapes ever so slightly. Stars that were orbiting peacefully begin to feel a pull from an unexpected direction. Gas clouds that were drifting along start to move in new ways. As the galaxies get closer, these effects become more pronounced. If you could watch a galactic merger in fast forward, compressing millions of years into minutes, you would see the galaxies stretching and warping like taffy being pulled. Long streams of stars get drawn out from each galaxy, forming what astronomers call tidal tails. These tails can extend for hundreds of thousands of light-years into space. Ghostly ribbons of stars marking the violence of the interaction. The first close pass is often not the final collision. Instead, the galaxies swing past each other, their mutual gravities slowing them down. They separate again, moving apart. But now they are bound together. Like dancers who have clasped hands, they cannot escape each other. Over the next few 100 million years, they swing back and forth, getting closer with each pass until finally they merge completely. During this process, something remarkable happens. The gas in both galaxies gets compressed by gravitational forces and shock waves. This compression triggers massive bursts of star formation. New stars light up by the billions, burning hot and bright. Astronomers call these events starbursts, and they can temporarily make a merging galaxy one of the brightest objects in its part of the universe. In some mergers, so much gas gets driven toward the centers of the galaxies that it falls into the supermassive black holes waiting there. This feeding frenzy causes the black holes to release tremendous amounts of energy,
shining as quasars that can be seen across billions of light-years of space. The cause of the merging galaxies blaze with the light of material being consumed by hungry black holes, outshining all the stars in both galaxies combined. Eventually, the chaos settles down. The two galaxies become one. The new combined galaxy is larger than either of its predecessors, but it also looks different.
The spiral arms that might have graced the original galaxies are gone, destroyed by the gravitational violence of the merger. What remains is typically an elliptical galaxy, smooth and featureless. Its stars orbiting in a complex tangle of different directions rather than in the orderly disk of a spiral. This is what happened to IC 1101, not once, but dozens and dozens of times. Each merger added stars, added mass, added material to the central black hole. Each merger erased more of whatever original structure the galaxy might have had. Over billions of years of this process, IC 1101 grew to become the monster we see today. Scientists can actually trace some of the evidence of these past mergers. When astronomers study the stars in IC 1101, they find populations of stars with different ages and different chemical compositions. These different populations are like geological layers in rock, each one recording a different era of the galaxy's history. Some stars are very old, likely members of the original galaxy that existed billions of years ago. Others are younger, formed during bursts of star formation triggered by mergers. Still others carry chemical signatures showing they were originally born in entirely different galaxies, foreign stars now absorbed into IC 1101's vast structure. The core of IC 1101 itself tells a story of violent history. As mentioned earlier, the core is enormous, stretching nearly 14,000 light-years across. But it is also unusually faint for its size. Scientists believe this is because repeated mergers, along with the activity of the central black hole, have scattered stars away from the very center. Here's what likely happened. When two supermassive black holes merge, they first form a binary system orbiting one another. As they spiral inward, they interact with nearby stars, flinging many of them outward at incredible speeds. This process, known as gravitational scouring, can clear out the central region of a galaxy, leaving it with fewer stars than expected. IC 1101 has undergone so many mergers that its core has been scoured again and again. The result is a massive core that is actually underpopulated compared to theoretical predictions. Scientists estimate that hundreds of billions of solar masses worth of stars may have been ejected from the core over IC 1101's lifetime. That is an extraordinary amount of stellar material, more than the total mass of many ordinary galaxies, thrown outward into the halo or even expelled completely. This kind of detective work is what makes astronomy so fascinating. We cannot visit IC 1101. We cannot send probes there or take samples. All we have is the light that reaches our telescopes. But from that light, we can deduce an incredible amount about what has happened over billions of years. We can read the history of the cosmos written in photons. Let me now expand our perspective even further. IC 1101 is the largest galaxy of a certain type that we have found. But the universe is full of extreme objects. Understanding where IC 1101 fits in the cosmic zoo of galaxies helps us appreciate just how remarkable it is. At one end of the size scale are dwarf galaxies. These are the smallest galaxies in the universe, containing anywhere from a few million to a few billion stars. Our own Milky Way has dozens of dwarf galaxies orbiting around it as satellites. The smallest of these, like Segway 1, contain only about 1,000 stars. They are so faint that astronomers did not even discover them until advanced surveys began in the 21st century. Dwarf galaxies play a crucial role in cosmic evolution. They are the building blocks from which larger galaxies are assembled. In the early universe, when the first galaxies were forming, most of them were dwarfs. These small galaxies then merged with each other over billions of years, building up the larger galaxies we see today. Every large galaxy, including the Milky Way, including IC 1101, started as dwarf galaxies that came together long ago. Moving up in size, we find galaxies like the Large Magellanic Cloud, which orbits our Milky Way at a distance of about 160,000 light-years. The Large Magellanic Cloud contains about 30 billion stars and has a diameter of about 14,000 light-years. It is visible to the naked eye from the southern hemisphere as a faint, cloud-like patch in the night sky. The Large Magellanic Cloud is actually being slowly absorbed by the Milky Way right now. Gas is being stripped from it, and eventually it will merge completely with our galaxy, adding its stars to our collection. This is galactic cannibalism in action, happening in our own backyard. Then we have galaxies similar to our own Milky Way. Spiral galaxies of this size typically contain between 100 billion and 400 billion stars, and have diameters of 100,000 to 200,000 light-years. They are common in the local universe, beautiful pinwheels of gas and stars, places where star formation continues even after billions of years. Our nearest large neighbor, the Andromeda Galaxy, is somewhat larger than the Milky Way. It contains about 1 trillion stars, maybe 2 or 3 times as many as our galaxy. Andromeda's disk stretches about 220,000 light-years across, making it roughly twice the diameter of the Milky Way. If you go to a dark location on a clear autumn night in the northern hemisphere, you can actually see Andromeda with your naked eye. It looks like a faint, fuzzy patch. But what you are actually seeing is the combined light of 1 trillion stars. The most distant object visible without a telescope. Beyond galaxies like Andromeda, we start to enter the realm of the giants. Some elliptical galaxies in the centers of galaxy clusters can contain several trillion stars and have diameters of hundreds of thousands of light-years. These are already among the largest objects in the universe, but they are still not as extreme as IC 1101. IC 1101 sits at the very top of this hierarchy. Its 4 to 6 million light-year diameter makes it roughly 20 to 30 times larger than the Andromeda Galaxy. Its 100 trillion stars would make it 100 times more populous than Andromeda. There simply are not many galaxies in the universe that can compare. There is one category of object that can challenge IC11 for one's claim to the title of largest galaxy, and that is the giant radio galaxies. These are galaxies with enormous jets of material shooting out from their central black holes. The jets can extend for millions of light-years into intergalactic space, making the total structure far larger than any collection of stars. The most extreme example discovered so far is a galaxy called Alcyoneus, announced in early 2022. Alcyoneus has radio lobes extending across an incredible 16 million light-years. That is roughly 3 times larger than IC 1101, making it the largest known structure created by a single galaxy. But here is the important distinction. Honius's enormous size comes from its jets, not from its stars. The actual body of the galaxy, the collection of stars and normal matter, is quite ordinary. It contains only about 240 billion solar masses of stars, far less than IC1ML1. The jets are impressive, but they are essentially empty space filled with very thin plasma and magnetic fields. They do not contain the trillions of stars that make IC1101 so massive. So when we talk about the biggest galaxy, we need to be clear about what we mean. If we mean the largest structure associated with a galaxy, then Alcyoneus and other giant radio galaxies take the prize.
But if we mean the largest collection of stars, the most massive body of a galaxy,
then IC1 is still the champion. There is another way to think about size that is worth considering. Instead of diameter, we could ask which galaxy has the most total mass. This turns out to be a complicated question, because most of a galaxy's mass is not in stars at all. It is in something we call dark matter. Dark matter is one of the greatest mysteries in modern physics. We cannot see it. It does not emit light or absorb light. It does not interact with normal matter except through gravity. But we know it exists because galaxies rotate in ways that would be impossible if they only contained the matter we can see. Here is the problem. If you add up all the stars in a galaxy and calculate how much gravitational pull they should have, you get a certain number. Then you measure how far stars are orbiting in the outer parts of the galaxy, which tells you how much gravity is actually present.
the two numbers do not match.
There is far more gravity than the visible matter can account for. The solution, according to most astronomers, is that galaxies are surrounded by vast halos of dark matter, material that we cannot see, but that makes up most of the galaxy's total mass. In a typical spiral galaxy like the Milky Way, dark matter accounts for about 90% of the total mass. The stars, gas, and dust that we can actually observe are just a small fraction of what is really there. IC1101 also has a dark matter halo, and it is correspondingly enormous. Scientists estimate that the total mass of IC1101, including its dark matter, could be as high as 1,100 trillion solar masses. That is about 100 times more massive than the Milky Way. This dark matter halo extends far beyond the visible stars of the galaxy. While the stellar body of IC1101 is already 4 to 6 million light-years across, the dark matter halo likely extends even further.
Some models suggest it could reach out tens of millions of light-years, making the complete structure of IC1 and its surroundings truly mind-boggling.
Understanding dark matter is one of the biggest challenges facing physics today. We know it is there because of its gravitational effects, but we do not know what it is made of. Many scientists believe it consists of some kind of particle that does not interact with light or normal matter, a particle we have not yet detected directly. Huge experiments are underway around the world trying to catch dark matter particles as they pass through Earth. So far, none have succeeded. The existence of dark matter shows us that even our understanding of something as large as IC1101 is incomplete. We can see the stars, we can measure the light, but 90% of what makes IC1101 the massive giant it is remains invisible to us, detectable only through its gravitational influence. There is still so much we do not know.
Before we continue, I want to spend some time exploring the remarkable technology and human ingenuity that allows us to study objects as distant as IC1101. It is easy to forget when we talk about a galaxy a billion light-years away
just how challenging it is to learn anything about such distant objects. The fact that we know as much as we do about IC 1101 is a testament to centuries of scientific progress and the dedication of thousands of researchers. The story of how we observe distant galaxies begins with the development of telescopes themselves. When Galileo first turned the primitive telescope toward the night sky in 609, he could see craters on the Moon and the moons of Jupiter. But distant galaxies were completely invisible to him. They were simply too faint, their light too dim to be detected by the small lenses of early telescopes. Over the next 300 years, telescopes grew larger and more sophisticated.
Bigger mirrors could gather more light, allowing astronomers to see fainter objects.
Better optics produced sharper images. By the time William Herschel discovered IC 1101 in 1790, he was using a telescope with a mirror about 18 inches across, enormous by the standards of his day. Even so, all he could see was a faint, fuzzy blob. He had no way of knowing what that blob actually was. The real breakthroughs came in the 20th century. Photography allowed astronomers to take long exposures, gathering light over hours, rather than relying on the human eye's ability to see in an instant. Spectroscopy allowed them to analyze the light from distant objects, breaking it into its component colors and deducing what elements were present and how fast objects were moving. Radio astronomy opened up entirely new windows on the universe, detecting radiation that human eyes cannot see. Each of these advances revealed something new about IC 1101.
Photographic plates showed that it was much larger than originally thought, extending far beyond what visual observers could detect. Spectroscopy revealed that it was moving away from us at tremendous speed, proving that it was extremely distant. Radio observations detected the jets from its central black hole, invisible to optical telescopes, but glowing brightly at radio wavelengths. Perhaps the most important development for studying distant galaxies was the launch of space telescopes. Earth's atmosphere, while essential for life, is a major obstacle for astronomy. The atmosphere absorbs certain wavelengths of light entirely, preventing X-rays and much of the ultraviolet and infrared spectrum from reaching ground-based telescopes. Even in visible light, the atmosphere shimmers and distorts, blurring images and limiting resolution. Space telescopes float above all of these problems.
The Hubble Space Telescope, launched in 1990, has been particularly important for studying galaxies like ICM Phenuan. With its position above the atmosphere, Hubble can capture images with incredible sharpness, revealing details that would be smeared out by atmospheric turbulence for ground-based observers. Hubble observations of IC 1101 have allowed astronomers to study the galaxy's core in unprecedented detail. They have measured the size and brightness of the central region, compared the distribution of stars to theoretical models, and looked for signs of recent stellar activity. The 2017 study that measured IC 11101's enormous core size relied heavily on Hubble data. Other space telescopes have contributed as well. The Chandra X-ray Observatory has mapped the hot gas surrounding IC 1101, revealing the environment in which this giant galaxy lives.
The Spitzer Space Telescope observed the galaxy in infrared light, detecting the glow of older, cooler stars that dominate elliptical galaxies. Each telescope, observing at different wavelengths, adds another piece to the puzzle. Ground-based telescopes have also improved dramatically. Modern observatories use a technique called adaptive optics, which uses deformable mirrors and lasers to correct for atmospheric distortion in real time. The result is images that approach the quality of space-based observations, but from telescopes that can be much larger than anything we could launch into orbit.
The largest ground-based telescopes today have mirrors more than 30 feet across, gathering enormous amounts of light and able to detect objects billions of times fainter than the unaided eye can see. These instruments can observe IC 1101 in exquisite detail, measuring the motions of stars, analyzing the chemical composition of different parts of the galaxy, and tracking changes over time.
Even more powerful telescopes are on the way. The James Webb Space Telescope, launched in late 2021, has already begun observing distant galaxies with unprecedented sensitivity in infrared light. The extremely large telescope, currently under construction in Chile, will have a mirror nearly 130 feet across when it sees first light in the late 2020s. These instruments will allow us to study IC 11101 and galaxies like it in even greater detail. There is also the question of how we measure the distances to objects as far away as IC 1101. Distance is one of the fundamental quantities in astronomy, but it is also one of the hardest to measure. How do you tell how far away something is when you cannot go there and stretch out a measuring tape? For relatively nearby objects, astronomers use a technique called parallax. As Earth orbits the Sun, our perspective on nearby stars changes slightly. By measuring how much a star appears to shift against the background of more distant stars over the course of a year, astronomers can calculate how far away it is. This works well for stars within a few thousand light years. But for more distant objects, the parallel shift is too tiny to measure, even with our most precise instruments. For more distant objects, astronomers use a cosmic distance ladder, a series of techniques that build on each other. One rung of this ladder involves a special type of star called a Tipheride variable. These stars pulsate in brightness in a regular pattern, and the period of their pulsation is directly related to their intrinsic luminosity. By measuring how bright a seed appears and how fast it pulsates, astronomers can calculate how far away it is. C variables can be seen in galaxies tens of millions of light-years away. But IC 1101 is too distant even for this technique.
At over 1 billion light-year, individual C-faint stars are far too faint to detect. For such extreme distances, astronomers rely on even brighter standard candles. One of the most important of these is a type of exploding star called a Type 1a supernova. These explosions occur when a white dwarf star accumulates too much matter from a companion and detonates in a thermonuclear explosion. Because the conditions for this detonation are similar from one supernova to another, they all reach roughly the same peak brightness. By measuring how bright a Type 1a supernova appears, astronomers can estimate how far away its host galaxy is. Another technique involves measuring the redshift of a galaxy's light. As the universe expands, light from distant objects gets stretched to longer wavelengths. This shifts the light toward the red end of the spectrum, hence the name redshift.
The more distant an object is, the more the universe has expanded since its light was emitted, and the greater its redshift.
By measuring the redshift of light from IC 1101, astronomers have determined that it is about 1.04 billion light-years away. This measurement, combined with observations of the galaxy's apparent size and brightness, allows them to calculate its physical properties, like diameter and stellar mass. Each of these techniques has uncertainties, and measuring cosmic distances is not a simple matter. Astronomers continue to refine their methods, using new observations and improved understanding of the underlying physics. The distance to IC 1101 might be revised as better data becomes available, but the basic picture of an enormous galaxy sitting over 1 billion light-years from Earth is well established. I also want to talk about what it means to observe something that is 1 billion light-years away. When we look at first 101, we are not seeing the galaxy as it is today. We are seeing it as it was over 1 billion years ago, when the light we detect today first began its journey toward Earth. 1 billion years ago, Earth was a very different place. Complex animal life had not yet evolved. The planet was populated by single-celled organisms, and perhaps simple multicellular life, but nothing that would be recognizable as an animal or plant. The continents were in different positions, gathered together in configurations that would be unrecognizable today. The atmosphere had a different composition. It was an alien world by any measure. During all the time since then, light from first 101 has been traveling through space. It crossed the vast emptiness between galaxies, occasionally passing through clouds of intergalactic gas or being bent slightly by the gravity of intervening objects. It traveled at the fastest speed anything can travel. Yet the distance was so immense that it took over 1 billion years to arrive. The IT 1101 we see in our telescopes might be very different from AC 101 as it exists right now. Over 1 billion years, much could have changed. Stars that were shining then might have burned out by now. New stars might have formed. The central black hole might have experienced new feeding events or gone through periods of dormancy. Galaxies that were falling toward IC 1101 1 billion years ago might have been consumed by now. We have no way of knowing what IC 1101 looks like at this very moment. The information about its current state will not reach us for another 1 billion years. In a very real sense, we are archaeologists of the cosmos, studying the past rather than the present. Every observation of a distant object is a look back in time, a glimpse of how things used to be rather than how they are now. This time delays both a limitation and an opportunity. It limits our ability to understand the current state of the universe. But it allows us to study cosmic history directly by looking at galaxies at different distances and therefore at different points in the past. Astronomers can piece together how galaxies have changed over cosmic time. We can see what galaxies looked like when the universe was young, compare them to more recent examples, and trace the evolution of cosmic structures over billions of years. IC 1101, seen as it was 1 billion years ago, provides a snapshot of a giant galaxy in a particular stage of its evolution. Other giant elliptical galaxies, some closer and some farther, provide additional snapshots. By combining all of these observations, astronomers build up a picture of how such galaxies form and change over time. Now, let me talk about something that fascinates me personally. The numbers we have been discussing are so vast that they become abstract. 100 trillion stars, 4 million light-years, 1 billion years. These are numbers that our brains evolved to handle poorly. We are adapted for counting small groups, measuring distances we can walk, tracking time spans of seasons and generations. Nothing in our evolutionary history prepared us for the cosmic scale. So, let me try a few more thought experiments to help make these numbers feel more real. Imagine you wanted to take a photograph of every star in IC 1101. You have a very fast camera that can snap 1 picture per second, and you never need to rest. How long would it take to photograph all 100 trillion stars? The answer is over 3 million years. If you started taking pictures when the first humans evolved, you would still have millions of years of photography ahead of you. Or consider this. The grains of sand on all the beaches of Earth number perhaps in the hundreds of trillions.
IC 1101 contains roughly as many stars as there are grains of sand on every beach on our entire planet. Each of those stars is a nuclear furnace, burning hydrogen into helium, releasing energy that streams outward in every direction. Each might have planets. Each has a story, a history, a future. Now imagine trying to walk across IC 1101. The average human walking speed is about 3 miles per hour. At that pace, walking 24 hours a day without stopping, it would take you about 50 trillion years to walk from one side of IC1 to the other. That is over 3,000 times longer than the current age of the universe. You could walk for the entire history of everything that has ever happened, from the Big Bang until now, and you would have covered less than 13,000ths of the distance across this single galaxy. Or think about communication. Light is the fastest thing in the universe, traveling at about 670 million miles an hour.
A message sent by light from one side of IC 111 would take 4 to 6 million years to reach the other side. If a civilization on one edge of IC 1101 sent a message to a civilization on the other edge, the receiving civilization would not get the message for millions of years, and any reply would take millions of years more to return. Communication across a single galaxy would span geological timescales. These thought experiments do not make the numbers truly graspable. Nothing can do that. The human mind simply is not built for cosmic scales. But they can give us a sense of the vastness, a feeling in our gut, even if not a true understanding in our heads. Let me now turn to a question that might be on your mind. If IC 1101 is so enormous, are there aliens living there? Could a galaxy that contains 100 trillion stars be home to intelligent life? This is the kind of question that science cannot answer directly right now. We have no way of detecting life in distant galaxies. We barely have the technology to look for life in our own solar system, let alone in galaxies a billion light-years away. But we can think about what the numbers suggest. If life requires planets and planets orbit stars, then a galaxy with more stars should have more potential homes for life. The Milky Way may contain somewhere between 100 billion and 400 billion planets. If even a small fraction of those are suitable for life, there could be millions of living worlds in our galaxy alone. Now scale that up to IC 1101. With around 100 trillion stars, this galaxy could host hundreds of trillions of planets. Even if only 1 in a billion of those developed life, that would still amount to hundreds of thousands of living worlds. And if only 1 in a trillion of those produced intelligent life capable of building civilizations, that would still mean around 100 civilizations within IC 1101. Of course, these figures are based on assumptions we cannot confirm. We don't know how common life truly is in the universe. We don't know how often it evolves intelligence. We don't even know for certain that life requires planets like Earth, or that it depends on water, or that it must be carbon-based. The range of conditions across the universe could be matched by an equally wide range of life forms. What we can say is that IC 1101 provides an immense stage for whatever processes might give rise to life. A galaxy of that size has been forming stars for billions of years. The heavy elements, carbon, oxygen, iron, that living systems rely on have been forged in stellar cores and spread by supernovae countless times. Whatever the recipe for life may be, IC 1101 has had vast ingredients and immense time to bring it into existence.
And if intelligent life does exist in IC 1101,
what might they think when they look up at their night sky? Their view would be very different from ours, where we see a relatively sparse field of stars, with a band of the Milky Way stretching across the heavens. They would see stars everywhere, in every direction. The density of stars in an elliptical galaxy like IC 1101 is much higher than in the disk of a spiral like ours. Near the center of IC 1101, the night sky would be ablaze with light. Stars would crowd so closely together that there might not be any true darkness at all. The glow of billions upon billions of nearby stars would fill the sky with a perpetual twilight. Navigation by stars would be impossible because there would be too many stars to distinguish one from another. Further out from the center, conditions would be more like what we experience, but still different. No spiral arms would trace patterns across the sky.
no central band of light would mark the plane of a galactic disk.
Instead, the stars would be distributed in a more spherical pattern, surrounding any observer in a shell of stellar light. Would such beings know about the history of their galaxy? Would they have discovered that their home was built from the remains of dozens of smaller galaxies consumed over billions of years? Would they have detected the enormous black hole at their galaxy center, or figured out that their cosmos was billions of years old? We cannot know. But it is fascinating to think that somewhere in 1C 1101, on one of hundreds of trillions of possible planets, intelligent beings might be asking the same questions about the universe that we ask here on Earth. They might be looking out at the surrounding space, seeing other galaxy clusters in the distance, wondering if those distant smudges of light contain other minds. They might even have detected our Milky Way, though from their perspective, it would be just another unremarkable spiral galaxy among billions. The universe is vast beyond comprehension, and the possibilities it contains are equally vast. Every galaxy we study reminds us of this vastness and challenges us to think about our place within it. Now I want to take some time to explore more about the environment that surrounds IC 1101, because no galaxy exists in complete isolation. IC 11101 sits at the heart of the Arbol 2029 galaxy cluster. And understanding this cluster helps us understand why IC 1101 became so enormous in the first place. Galaxy clusters are some of the largest gravitationally bound structures in the universe. They can contain hundreds or even thousands of individual galaxies, all orbiting around a common center of mass. The space between galaxies in a cluster is not empty. It is filled with extremely hot gas, heated to temperatures of tens of millions of degrees by the gravitational energy released as the cluster formed. Arbol 2029 is what astronomers call a relaxed cluster, meaning it has settled into a fairly stable configuration over billions of years. The galaxies within it have had time to sort themselves out, with the most massive ones sinking toward the center due to a process called dynamical friction. As more massive objects move through a sea of smaller objects, they experience a kind of drag that slows them down and causes them to spiral inward. IC 11101 sits at the very bottom of this gravitational well, at the densest part of the cluster where galaxies are packed most tightly together. This location is not a coincidence. IC 1101 grew so large precisely because it was in this privileged position. As other galaxies spiraled toward the cluster center, they encountered IC 1101 and were absorbed.
The same process that brought IC 1101 to the center also brought it a constant supply of victims to consume. The hot gas that fills the cluster also plays a role in IC 1101's evolution. This gas, called the intracluster medium, is incredibly sparse by normal standards. If you could scoop up a cubic meter of it, you would find only a few atoms. But because there is so much of it, spread over millions of light years, it adds up to an enormous amount of mass. This gas is so hot that it emits X-rays, which is how astronomers detect it. X-ray telescopes like NASA's Chandra Observatory have mapped the distribution of this hot gas in Hubble 2029, revealing that it is concentrated around IC 1101 at the cluster center. The gas forms a kind of atmosphere around the giant galaxy, a thin haze of super-hot particles extending millions of light years into space. The presence of this hot gas has implications for IC 1101's future.
Hot gas can cool down over time, radiating away its energy as X-rays. When it cools enough, it can fall into the central galaxy and potentially fuel new star formation. In some galaxy clusters, astronomers have observed enormous flows of cooling gas, hundreds of solar masses worth per year, streaming into the central galaxy. But in IC11's case, something seems to be preventing this cooling flow from igniting a new burst of star formation. The leading theory is that the supermassive black hole at IC 11101 center is responsible. When gas falls toward the black hole, some of it gets heated up and blown back out into the cluster. This creates a feedback loop where the black hole regulates the gas supply, preventing too much from accumulating and forming stars. We can actually see evidence of this feedback in observations of IC 1101 and its surroundings. There are cavities in the hot gas around the galaxy, bubbles that have been blown by jets from the central black hole.
These cavities are millions of light years across.
Enormous voids carved out of the intracluster medium by the energy output of the black hole. This feedback mechanism is thought to be important for understanding why massive elliptical galaxies like IC 1001 are not forming stars today. Without the black hole regulating the gas supply, cooling flows would deliver enough material to trigger substantial star formation. But the black hole acts like a thermostat, heating up gas whenever too much starts to cool, keeping the galaxy in a kind of permanent energy balance. The interplay between galaxies, their black holes, and the hot gas in galaxy clusters is one of the most active areas of research in modern astrophysics. Scientists are still working out the details of how this feedback works, how it varies from cluster to cluster, and what it means for the long-term evolution of the universe's largest galaxies. Let me now take you through a timeline of IC 1101's history as best we can reconstruct it from observations and theoretical models. This timeline spans billions of years and involves processes that are difficult to imagine. But understanding it helps us appreciate how this cosmic giant came to be. The story begins about 13 billion years ago, not long after the Big Bang itself. The universe at that time was very different from what we see today. There were no galaxies yet, just vast clouds of hydrogen and helium gas left over from the first few minutes of cosmic history. These clouds were not perfectly uniform. Some regions were slightly denser than others, and gravity began to pull these denser regions together. Over the first few 100 million years, these denser regions collapsed to form the first stars and the first primitive galaxies. These early galaxies were small, irregular collections of stars, nothing like the grand spirals and ellipticals we see today.
They formed in the densest parts of the cosmic web, the network of filaments and nodes that define the large-scale structure of the universe. The region of space that would eventually become the Able 2029 cluster was one of these dense regions. Many small galaxies formed there, and they immediately began interacting with each other. Merges happened frequently in the early universe when galaxies were closer together and the cosmic web was more compact than it is today. One of those early galaxies, or more likely a merger product of several early galaxies, was the ancestor of IC 1101. We do not know exactly what this protogalaxy looked like, but it was probably a collection of a few billion stars, maybe a 100,000 light-years across, with a growing black hole at its center. Over the next several billion years, this protogalaxy experienced merger after merger. Each time a smaller galaxy wandered too close, gravity captured it and eventually absorbed it.
Each merger added stars and gas, and each merger fed the central black hole. The galaxy grew larger and larger, and its position at the center of a dense region ensured a steady supply of victims. By about 10 billion years ago, the ancestor of IC 1101 had probably already become a giant elliptical galaxy, having experienced dozens of major mergers. It would have been one of the largest galaxies in its part of the universe even then, though not yet as massive as it is today. The next several billion years saw continued growth, though at a slower pace. The most intense period of galaxy formation was winding down across the universe. Star formation rates were declining as galaxies used up their gas supplies. Merges became less frequent as the expansion of the universe carried galaxies farther apart. But IC 11101 was in the special location. The Able 2029 cluster had grown and matured, and IC 1101 sat at its heart.
Galaxies continued to fall toward the cluster center, drawn by the enormous combined gravity of all the matter there. And when they reached the center, they encountered IC 1101. During this period, IC 1101 probably experienced another 20 or 30 major mergers, along with countless minor ones. Each merger added to its mass. Each merger stirred up its stars. Each merger fed its already enormous black hole. By about 5 billion years ago, IC 1101 had grown to something close to its current size. It contained tens of trillions of stars, spread across millions of light-years of space. Its black hole had grown to tens of billions of solar masses, and it had essentially run out of easy prey. The galaxy that remained in the cluster were either too far from the center to be captured easily, or were locked in stable orbits that would take many more billions of years to decay. IC 11101 had consumed most of what it could consume. Its days of rapid growth were over. What remains today is what we observe. A dying giant, still enormous, still magnificent, but no longer growing. Its stars are old, its gas is depleted, its black hole is relatively quiet, occasionally flaring up when a bit of gas wanders too close, but mostly dormant. IC 1101 has reached something like a steady state, slowly fading as its stars burn out one by one. This history is not unique to IC 1101. Many giant elliptical galaxies at the centers of clusters have similar stories. But IC 1101 represents an extreme case.
A galaxy that was in the right place at the right time to grow to truly exceptional proportions. Not the only giant in the universe, but one of the very largest we have found. As I bring us toward the end of this exploration, I want to reflect on what IC 11101 means for our understanding of the universe and our place within it. The universe is hierarchical. Small things combine to make larger things. Atoms form stars. Stars form galaxies.
Galaxies form clusters. Clusters form superclusters.
This hierarchical structure is one of the defining features of the cosmos we live in, a consequence of how gravity operates over cosmic time. IC 11101 represents the upper end of this hierarchy for individual galaxies. There may be larger structures in the universe, vast walls and filaments of galaxies stretching for hundreds of millions of light years. But when it comes to single objects bound together by their own gravity, giant galaxies like IC 1101 are as big as it gets. Understanding the limits of cosmic structures teaches us about the underlying physics of the universe. The fact that IC 1101 is about 4 to 6 million light-years across, rather than a billion light-year across, tells us something about how gravity and dark matter and cosmic expansion all balance against each other. If any of these factors were different, the largest galaxies might be much larger or much smaller than what we actually observe. In a sense, IC 1101 is a message from the universe about its own nature. By studying this giant galaxy, we learn about the rules that govern everything from the smallest atoms to the largest structures. We learn about how time and gravity and energy have shaped the cosmos over billions of years. There is also something humbling about IC 1101. We tend to think of ourselves as significant, our lives and our world as important, and in many ways they are. But IC 1101 reminds us that the universe operates on scales far beyond anything in human experience. A galaxy with 100 trillion stars sitting a billion light-years away, utterly indifferent to our existence. We are specks on a speck, orbiting a speck in a galaxy that is itself just a speck compared to the true giants of the cosmos. Yet somehow, those specks have figured out that IC 11101 exists. We have measured it, studied it, understood it. We have placed it in context, tracing its history back billions of years and projecting its future trillions of years hence. From our tiny vantage point on a rocky world around an ordinary star, we have reached out with our minds to comprehend objects of incomprehensible size and age. Let me share a few more thoughts about what IC 1101 teaches us about the nature of existence and our place within it. First, consider the improbability of our situation. For consciousness to emerge at all required an extraordinarily specific sequence of events. The Big Bang had to produce matter in just the right proportions. That matter had to clump together into galaxies and stars. Stars had to forge heavier elements in their cores and scatter them through supernovas. Planets had to form from those scattered elements. On at least one of those planets, chemistry had to become complex enough to produce self-replicating molecules. Those molecules had to evolve over billions of years into creatures capable of thought, curiosity, and scientific investigation. Each step in this chain was contingent on the ones that came before. If any of countless variables had been slightly different, we would not be here to contemplate IC 1101. The conditions that allow for intelligent observers to exist are surprisingly narrow, and the fact that we exist at all is something close to miraculous. Now consider what we do with that existence. Of all the things humans could wonder about, we choose to wonder about the stars. We build enormous telescopes, launch satellites into orbit, dedicate careers to understanding objects we will never touch. We invest tremendous resources and effort into answering questions that have no practical application whatsoever. Why do we do this? I think it is because there is something fundamental in human nature that needs to understand.
We are pattern-seeking, question-asking, meaning-making creatures. We cannot look at a mystery and not want to solve it. The existence of IC 1101, so vast and so far away, is perhaps the ultimate expression of the mysterious universe we inhabit. And our drive to understand it is perhaps the ultimate expression of what makes us human. There is a famous photograph called the Hubble Deep Field, taken in 1995. The Hubble Space Telescope pointed at a tiny, seemingly empty patch of sky about the size of a grain of sand held at arm's length. It gathered light from that patch for over 100 hours. What the resulting image revealed was astounding. That tiny patch of sky contained about 3,000 galaxies, each one an island universe containing billions of stars. Since then, even deeper images have been taken. The Hubble Ultra Deep Field, the Hubble Extreme Deep Field, and most recently, images from the James Webb Space Telescope have revealed ever more galaxies in ever smaller patches of sky.
The conclusion is inescapable. Everywhere we look, no matter how small the area of sky, we find galaxies. The universe is filled with them, perhaps 2 trillion in total, spread across billions of light years in every direction. IC 1101 is just one of those 2 trillion galaxies. It is an exceptional one. Yes, larger and more massive than almost all the rest. But it is still just one galaxy among countless billions. The fact that we have singled it out, studied it, and come to understand it is a testament to human curiosity and ingenuity. But we could have chosen almost any galaxy and found wonders just as remarkable. The universe is generous with its marvels. I also want to reflect on what it means to know something about IC11 that no human being knew just a few centuries ago. William Herschel, when he first spotted this object in 1790, could have had no conception of what he was looking at. He saw a fuzzy blob. We see 100 trillion stars, a 50 billion solar mass black hole, billions of years of cosmic history. The difference between his understanding and ours is almost as vast as the distance to IC 1101 itself. This progress in understanding did not happen automatically. It required countless individuals contributing their pieces to the puzzle. Astronomers who built bigger telescopes, physicists who worked out the theories of light and gravity, engineers who designed satellites and instruments, mathematicians who developed the tools to analyze data. Each generation built on the work of those who came before, gradually constructing the edifice of knowledge that allows us to comprehend objects a billion light years away. When you think about IC 1101, you are not just thinking about a galaxy. You are participating in a tradition of inquiry that stretches back centuries. You are standing on the shoulders of giants.
As Newton once said, seeing farther because of the accumulated efforts of all who came before.
The understanding of 1C1101 is not the property of any individual. It belongs to humanity as a whole, a shared heritage of knowledge that transcends any single person or nation. There is something deeply democratic about this. Astronomical knowledge is available to anyone who wants it,
You don't need wealth or power to learn about 1C1101. The knowledge is already out there in books, articles, and videos like this, waiting quietly for anyone curious enough to reach for it. The universe doesn't hide itself behind status or borders. It reveals itself to those who ask. And there's something deeply comforting in that. In a world that can often feel divided, the pursuit of understanding the cosmos is something that brings us together. It doesn't matter where you're from or what language you speak. The stars shine for everyone. And the truth about 1C1101 is the same everywhere.
Science at its best is a shared journey, a quiet collaboration across continents and cultures. People looking up at the same sky, asking the same questions, building something larger than any one person could alone. And beyond the facts, there is something else worth holding on to: wonder. The idea that IC1101 stretches 4 to 6 million light-years across is impressive. But the feeling it creates, that quiet sense of awe, is something deeper. It's not just information, it's an experience. Wonder is often treated as something childish, something we're meant to outgrow. But maybe it's the opposite. Maybe wonder is essential. It opens us to something beyond the routine of everyday life. It reminds us that existence is larger, richer, and far more mysterious than the small circle of our daily concerns. It connects us to something larger than ourselves.
IC1101 is an occasion for wonder. If anything is 100 trillion stars, 4 to 6 million light-years, a billion years of light travel, time, a supermassive black hole containing 50 billion solar masses, numbers so large they strain comprehension, distances so vast they beggar imagination. If you can contemplate these things without feeling a sense of awe, I am not sure what would move you. But wonder does not require understanding. You can feel wonder at IC1101, even if you do not grasp all the science behind it. The sense of vastness, the confrontation with scales beyond human experience, the realization of how much exists beyond our small world. These are available to anyone who takes the time to really think about what we have discussed. Science enhances wonder by revealing the specifics, but wonder itself is a fundamentally human response to the immensity of creation. That is the true wonder of science and of astronomy in particular. Not just the objects we study, magnificent as they are, but the fact that we can study them at all. Consciousness looking out at the cosmos and making sense of what it sees. Matter understanding itself. I want to leave you with one final thought. The atoms in your body were forged in stars. The carbon that makes up your muscles, the oxygen you breathe, the iron in your blood. All of these elements were created in the nuclear furnaces at the cores of stars that lived and died before our sun was born. When those ancient stars exploded as supernovas, they scattered their elemental riches across space. Eventually, some of those atoms found their way into a cloud of gas and dust that collapsed to form our solar system. They became the Earth, and then, after billions of years of evolution, they became you. You are made of star stuff. This is not poetry. It is chemistry. The very same processes that light up IC1101's 100 trillion stars also created the matter from which you are assembled. There is a direct physical connection between you and those distant fires. In a very real sense,
When you contemplate IC 1101, you are star stuff contemplating more star stuff. The universe is looking at itself, trying to understand what it is and how it came to be. We are not separate from the cosmos we study. We are part of it, and our curiosity is the cosmos being curious about itself. IC1 will never know that we have discovered it. Galaxies do not have minds or experiences, but we know. And in knowing, we complete a circuit that connects human consciousness to cosmic grandeur. We are tiny, yes. We are brief, yes. But in the brief moment of our existence, we can reach out across 1 billion light years and touch the largest galaxy ever discovered. That reach is our glory. When you next look up at the night sky, remember IC 1101.
You cannot see it with your eyes. It is far too distant and too faint for human vision.
But it is there, in the direction of the constellation Virgo, shining with the light of 100 trillion stars. It has been there for billions of years, and it will remain there for billions more. Long after our sun has burned out, long after Earth has been consumed by an expanding red giant, IC 1101 will still be there, slowly fading into the cosmic night, but not yet gone. We are part of a universe that contains such wonders. We are made of the same stuff as IC 1101 stars, formed by the same processes, governed by the same laws of physics. In studying that distant giant, we learn about ourselves and our place in the grand story of cosmic evolution. The biggest galaxy we have ever discovered is bigger than your imagination. But the fact that you can imagine it at all, that you can hold in your mind a picture of 100 trillion stars spread across millions of light years, that you can wonder about its past and future and inhabitants. That is perhaps the most amazing thing of all. Thank you for joining me on this journey through the biggest galaxy ever discovered. If this video helped you see the universe in a new way, please consider leaving a comment letting us know what you think about our place in a cosmos that contains such wonders. And if you want to keep exploring the mysteries of the universe with us, do not forget to like this video and subscribe to the channel. Until next time, keep looking up and keep wondering.